Okay, this video is going to cover the trig review at the end of pre-calculus. The reason for this trig review is there is a lot of trig that's included in calculus. And a lot of it is stuff that you'll be required to know how to do without a calculator. So that's what we're going to try to just go over things we did first semester in trig. First of all, in trig, to do things without a calculator, you use the unit circle. There's some different things we're going to need to know to use the unit circle, and we'll talk about those here. One is, you already know the SOHCAHTOA thing. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. Then the reciprocal ones, cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. Now you also can use, to help use the unit circle sometimes, you can use the x, y, and r. So those are just used to replace the adjacent, opposite, and hypotenuse. And all you have to remember is x is always the adjacent side, y is always the opposite side, and r is always positive. And you can use those. Now in calculus, almost all of the angles will be measured in radians. Now in trig, we did it in degrees and radians to get used to doing radians, but it's almost always in radians in calculus because you will always have in the same problem, almost always, x as a variable, and you'll have a trig function like the tangent of x. Anytime you have both of those things in a problem where x is just a number and x is the angle on a trig function, you have to be in radians. So the key in radians is to remember that pi radians is the same as 180 degrees. So if we convert them, if you remember doing this in trig, if you want to go to degrees to radians, you take whatever the degrees are and multiply by pi over 180. And then usually it's a fraction, you simplify the fraction. To go the opposite direction from radians to degrees, you take the number of radians times 180 degrees over pi. So you flip it over. Usually if there's a pi in it, which there usually will be, that'll just cancel out the pi and you go from there. So some common angles, as I mentioned, pi is 180. So pi over 6 would be 180 minus 6 is 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees. Pi over 2 is 90 degrees. 3 pi over 2 is 270. 2 pi is 360. They'll also use negative angles a lot in calculus, like negative pi over 2 is the very common one. We also talked in trig about standard position. Usually draw angles in standard position, which means you start on the positive x-axis and you go counterclockwise to do the angle. And if you go clockwise, then it's a negative angle. So like here, if we just want to draw these, like 5 pi over 4. Well, if we want to draw that, we know all the way around to right here is pi. Well, pi is the same as 4/4. So 5/4 would be a little farther. So 5/4 pi is down here. Or 2/3 pi. We draw that. Well, all the way to here is pi, again, which is 3/3. It's really helpful to think in terms of common denominators. So that means 2/3 pi must stop here somewhere. A negative 11 pi over 6, so it's negative, so we go backwards. Well, all the way around backwards, all the way around to here would be 2 pi, which would be 12/6. So a negative 11/6 is going to stop a little short, so it's over here somewhere. And then negative 3 pi over 2, again, that's backwards. So if we go backwards, that'd be pi over 2, 2 pi over 2, 3 pi over 2 would be right here. So that's how we draw those. It's really helpful to think in terms of common denominators and to do it in terms of radians and not always be converting in your head to degrees. The next thing to use the unit circle is we have 3 things we need to use. We have 2 special right triangles. You did these in geometry, we did these in trig. One is a 30, 60, 90 triangle. Now here, I put those down in radians. So 30 is pi over 6, 60 is pi over 3. There's our right angle. In a 30, 60, 90 triangle, opposite pi over 6 is the short leg. If you think of that as 1, opposite pi over 3 is the long leg. It's the short leg times radical 3. So if that's 1, this is radical 3. Then the hypotenuse is 2. If you did the Pythagorean theorem, you'd see it works out that the hypotenuse is 2. So we can use these sides always for this type of triangle. So like here, the sine of pi over 6, we know sine is opposite over hypotenuse, 1 over 2. Cosine of pi over 6, adjacent over hypotenuse, radical 3 over 2. Tangent of pi over 6, opposite over adjacent, 1 over radical 3. Then the reciprocal functions. Cosecant is the reciprocal of sine, so 2 over 1 or 2. Secant is the reciprocal of cosine, 2 over radical 3. Cotangent is the reciprocal of tangent, radical 3 over 1 or just radical 3. So that's for pi over 6. We can do the same thing for the other angle there, the other acute angle, pi over 3. Again, sine is opposite over hypotenuse, so radical 3 over 2. The cosecant is the reciprocal of sine, so 2 over radical 3. Cosine is adjacent over hypotenuse, 1 over 2. So secant is the reciprocal of that, 2 over 1 or 2. Tangent is opposite over adjacent, so radical 3 over 1 or just radical 3. So the cotangent is the reciprocal of that, so 1 over radical 3. So that's for pi over 3 and pi over 6. Now we also have a triangle for a 45, 45, 90 triangle. As we mentioned before, 45 degrees is the same as pi over 4. So if you get an angle that's pi over 4, you can use this triangle. The two legs are always the same because this is an isosceles triangle, so we can use 1 for each of those. And the hypotenuse, you can get from Pythagorean theorem, is radical 2. So same way, sine is opposite over hypotenuse, 1 over radical 2. Cosine is adjacent over hypotenuse, always also 1 over radical 2. Tangents opposite over adjacent, 1 over 1. The reciprocal functions, cosecant is the reciprocal of sine, radical 2 over 1 or just radical 2. Secant is the reciprocal of cosine, radical 2 over 1 or just radical 2. And cotangent is the reciprocal of tangent, just 1. So those are the special right triangles. Whenever you see pi over 6, pi over 3, pi over 4, use those triangles. You will need to know those. There's a part on the AP Calc test that is a no calculator part, and they will have problems where you'll have to use these facts. The other thing that could happen is instead of getting one of these three angles, you could get an angle that lies right on one of the quadrant lines. Those are called quadrantal angles. There's a couple ways to do that. The way we did them in trig was we picked a point. So you pick a point that's on one of those quadrant lines. The easiest ones to pick are ones that are 1 unit away from the origin. Everything just works out easier. So at 0 or 2 pi, we could use the point 1, 0. And then if you think in terms of x, y, and r, remember x is 1, y is 0, and the radius is 1. At pi over 2, we use the point 0, 1. X is 0, y is 1, r is 1. At pi or negative pi, we use negative 1, 0. X is negative 1, y is 0. At 3/2 pi or negative pi over 2, we use 0, negative 1. On each one of them, r is 1. Remember, r is always positive because it's just a length. So using that and remembering that x is always adjacent, y is always opposite, the sine of pi over 2, well, sine is going to be y over r, so 1 over 1. The cosine is going to be x over r, so 0 over 1, or 0. The tangent is y over x, so it's 1 over 0, which is undefined. Cotangent is the reciprocal of tangent. Since the tangent was 1 over 0, the cotangent is 0 over 1, which is 0. Or cotangent is x over r. If we go to a negative pi over 2, well, negative pi over 2 is down here. Sine, again, is y over r. That's opposite over hypotenuse. That's negative 1 over 1, which is negative 1. The cosine is x over r, so 0 over 1. The tangent is y over x, negative 1 over 0, which is undefined. The cosecant is the reciprocal of sine. The reciprocal of negative 1 is negative 1. If we go to pi, well, pi is over here. We use the point -1, 0. So sine is y over r, 0 over 1. Cosine is x over r, -1 over 1, which is -1. Tangent is y over x, which is 0 over -1, which is 0. Remember, secant is the reciprocal of cosine. The reciprocal of -1 is still -1. 2 pi. Well, 2 pi is the same as 0. They will have all the same trig functions. We use the point 1, 0. The sine is y over r, so 0 over 1 or 0. Cosine is x over r, so 1 over 1 or 1. The tangent is y over x, so 0 over 1, which is 0. Cotangent is the reciprocal of tangent, which would be 1 over 0, which is undefined. Okay? Then, a big place this is used, as I mentioned, is to find the trig functions for any angle without a calculator. To do that, use reference angle. Remember from trig, a reference angle is an acute angle. It's always an acute angle. It's always measured to the nearest x-axis. So wherever that terminal side of that angle is, remember the terminal side is where the angle ends up. It's always measured to the nearest x-axis. So what you do is draw the angle in the correct quadrant. So like if we were doing this in the cosine of 4 pi over 3, the first thing we want to do is draw the angle in the correct quadrant. So this would be 3/3 pi to right here. So pi is the same as 3/3. So 4/3 is going to be a little farther, so it's going to be down here. Then we draw a triangle. We always draw our triangle to the x-axis. Now we need to find our reference angle. Well, this is 3/3, this is 4/3, or this is 1/3. Well, we already did the sides of a triangle when we have pi over 3. The opposite side is radical 3. The adjacent side is 1. The hypotenuse is 2. Now it's important to remember to put your negatives in. Since this 1 is left, that's negative. Radical 3 is down, it's negative. There's the sides we're going to use. So now, if we're finding cosine, we know cosine is adjacent over hypotenuse, so our cosine is -1/2. So we drew the triangle in the correct, we draw our angle in the correct quadrant, drew the triangle to the nearest x-axis, found the reference angle, then we filled in the sides and used those to find the trig ratio. Or this one, the tangent of 5 pi over 6. Again, first thing we do is draw the angle in the correct quadrant. Well, all the way around here is pi, which is 6/6. So we want to stop a little short. We're going to go to 5/6. Draw our triangle down to the x-axis. Find the reference angle. Well, 5/6 to 6/6 is 1/6, so this angle here is pi over 6. Now in our triangle, opposite pi over 6 is 1. The adjacent side is radical 3. The hypotenuse is 2. Since this one's left, we're going to make it negative. Now we're doing tangent. Tangent is opposite over adjacent, so it's 1 over negative radical 3 for our tangent. Or this one, the cosecant of 7/4 pi. Again, first thing we want to do is draw that. Let's see, all the way around would be 2 pi, which is 8/4. So if we want 7/4, we're going to stop short. So we're going to stop over here somewhere. So here's 7/4. Well, 7/4 to 8/4 is 1/4, so that's this angle here. And we have pi over 4. The two sides of the legs are the same, so 1 and 1. The hypotenuse is radical 2. Now don't forget this one is down, so that's a -1. Then we're finding cosecant. Well, cosecant is the reciprocal of sine. Sine would be opposite over hypotenuse, which would be -1 over radical 2. So the cosecant is radical 2 over -1, which is just negative radical 2. This one is secant of negative pi over 6. Again, let's draw it first. Negative pi over 6, that's negative, so going backwards, so pi over 6 is just down here somewhere. We draw our triangle up to the x-axis. Let's see if this is negative pi over 6 and this is 0. From 0 to negative pi over 6 is pi over 6. So that's our reference angle. Again, opposite pi over 6 is always 1. The adjacent is radical 3. Hypotenuse is 2. Since this was down, it's negative. Now we're doing secant. Secant is the reciprocal of cosine. Well, the cosine would be adjacent over hypotenuse, or radical 3 over 2. So secant is 2 over radical 3. So that's how you use the unit circle on those type. Now we mentioned with quadrantal angles, we can pick a point. Another way to do that, if you remember the graphs that we did in trig, sometimes that can be an easy way. And you don't have to do in depth, just remember things about the graph, like a sine curve. A sine curve starts at 0, over a period at 2 pi at 0, in the middle at 0. Then in the left half, it's up at, that'd be pi over 2, it's up at 1. In the right half at 3/2 pi, it's down at negative 1. If you can just draw that much, that makes it pretty easy to find the quadrantal angle. If you remember how that works, you do the sine of negative pi over 2. Well, you know if it's at 0, at negative pi, it's back at 0. So in between there at negative pi over 2, it's down at negative 1. The cosine curve starts with a crest, so it's at 0, its value is 1. Over a period at 2 pi, it's 1. So in the middle at 1 pi, it would be a negative 1. Then in the left half, it'd be between there. At pi over 2, it'd be 0. In the right half, at 3 pi over 2, it would be 0 again. So if we were doing the cosine of pi over 2, you could think, okay, we go from a positive 1 to negative 1, so right in the middle, we're at 0. Then the tangent curve, remember the tangent curve looks like this. So right at the origin, right at 0, it's got an axis point, so it's 0. It only has a period of pi, so if we went over to pi, there'd be another 0, or at negative pi, there would be a 0. So right in between those is an asymptote, so at pi over 2 and negative pi over 2, it's undefined. And in between there, at pi over 4, it's got an amplitude at 1. At negative pi over 4, it's down at negative 1. So if we were doing the tangent of 2 pi, well, see, we know at 0, it's 0. At pi, it's 0. So at 2 pi, it's also 0. You may not use that, but sometimes that can be handy, especially with sine and cosine. If you remember how the graphs work, it can be a real easy way to do it. Okay? The third part of this review is The third part of this review is, we'll just use this one, is some identities. I know you loved identities when we did them in trig, but there are some of them that pop up sometimes, usually not at the beginning of calculus, but a little later when you get into what's called antiderivatives or integrals. You'll need some identities to convert things. Just some of the basics. So like we did the Pythagorean identities. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals cosecant squared. Cotangent squared equals cosecant squared minus 1. We did the double angle and half angle. These are actually the same thing. They've just kind of solved for different things. So like the double angles, the sine of 2 theta is 2 sine theta cosine theta. Cosine 2 theta, there were 3 possibilities. Cosine squared minus sine squared, 1 minus 2 sine squared, and 2 cosine squared minus 1. I didn't include the tangent ones because I don't see those come up much in calculus. Half angle, if you just take those and solve for something like sine squared is 1 minus cosine 2 theta over 2, cosine squared 1 plus cosine 2 theta over 2. The shift identities, I don't think we talked about these much, but remember, if you shift these over, like the sine of theta, if you move over right pi over 2, that's the same as a cosine curve. If you took a cosine curve and moved it over pi over 2, that's the same as a negative sine curve, because it's like it flips it over. We talked about negative angles. 2 of them work the way you would think. The sine of a negative theta is negative sine theta, which seems logical. Tangent of negative theta equals negative tangent theta. Seems logical. The one that you have to remember is the cosine of a negative theta is actually the same as the cosine of theta because of how the graph works, how the quadrants work. Then product to sum. Here you just have to match this up. 2 sine A cosine B. If you want to change from a product to a sum, you just figure out what A and B are and plug those numbers in. Same 2 cosine A cosine B. So if you see 2 cosine cosine, figure out what A and B, plug those in. Same with 2 sine A sine B. Figure out A and B and plug them in. So some examples here. If in a problem you had sine squared and I said, I need that not to be squared. what can we do? Well, you look up here and look for a sine squared. Well, if you notice this half angle one here, we have a sine squared. It says it's 1 minus cosine 2 theta over 2. Well, there's no exponent there, so we just use that one. Or this one. Notice it says we're converting this from a product to a sum. So, product to sum. Now notice, these all had a 2 in front. This doesn't. So the first thing to do is we need to put a 2 in front. Well, if we put a 2 in front of that, and I put all that in parentheses, I need to put a half out front to make that all work out, because 1/2 of 2 cancels out. But we need that 2 so it matches the identity. So we need to figure out, we look up here, there's sine A cosine B, and that's what we have. We need to figure out what A and B are. Well, it looks like A matches up with 3x, B matches up with 2x. So we go to the right side, that's the sine of A plus B, that's the sine of 3x plus 2x. The sine of A minus B, that's 3x minus 2x. Notice the half is still out front. So we simplify a little bit. 3x plus 2x is 5x. 3x minus 2 is 1x. So we converted this from a product. Now you can see it's a sum. That's all there is to it. This one's a little trickier. Here I have sine cubed x cosine squared x. Well, what if I want to get rid of any of the exponents there? Well, first, we haven't seen a sine cubed anywhere in the identities, but we could think of sine cubed as sine times sine squared. So if we break it down like that, now we look up identities. Well, the sine can stay because it doesn't have an exponent. The exponent's 1. Sine squared, well, we could go back up and use the half angle again. Sine squared is 1 minus cosine 2x over 2, so we put that in. Cosine squared, we can go find that. That's 1 plus the cosine of 2x over 2. We can put that in. So now we've converted it. Now, you see, we don't have any more exponents bigger than 1. Okay, the identity ones, they'll come a little later usually in calculus, but the other ones come right off the bat. And that's it. Thank you.